Dr. Krishna Prasad Dolly. I would call upon Shobha Singh for the co-chair, Senior Divisional Geologist from Department of Mines and Geology. And I would like Mrs. Urusha Sharma Pandey and Mrs. Ashima Bartola to help chair and co-chair as a reporter for this session. Again, I would like all the participants to come and take your chair so that we can start our session. With this, I would like to hand over the mic to the chair to start the session and to call upon the presenters accordingly. Thank you.
So now we will start our first session of this conference, 9th Geological Congress Kathmandu, which is being held in Kathmandu. In the first session, we have two paper presenters. One of the presenters is Madam Professor Mary Hubbard, who will be making a presentation on understanding faults and shear zones in the Himalayas, the necessity of multidisciplinary approach. Professor Mary.
Thank you. In the interest of time, I'm going to get started. And I'm starting up here just so I can see your faces. And I also want you to confirm that you can hear me. Yes, yes. I'll be jumping down so that I can see what I'm presenting, lest I forget. But I just want to say thank you for coming, and thank you for this great honor of being the first presentation here at this conference. So thank you all to the organizers. I've got this presentation listed, and it's in the abstract as an authored presentation. However, I want to say that many people have helped me out in the work that I'm going to present. And I'm going to present some things that are historical going back to my PhD work here a long time ago, as well as some more recent work, but it's all with collaborators. I want to thank many people. I also want to thank the senior geologists that have come before me. So I've listed a few names here. It's not exhaustive by any means. And I want to thank the students that I've had the pleasure to work with, because you are the future of the geosciences. So thank you to all of you. I'd like to dedicate this presentation to the Trichandra campus and Tribhuvan University, because these institutions, or this institution, welcomed me here 33 years ago as a young and somewhat naive student. It also hosted me graciously last year when I was here on a Fulbright fellowship. So I feel indebted to the Trichandra campus at Tribhuvan University. I also want to thank the Department of Mines and Geology for the work that they've done and for the help that they've provided in getting samples back to the US for analyses. Recently, I read my journal from 1985 about my first visit to the Department of Mines and Geology to get the permission letter, and it was very interesting reading. So with that, let me move on. I'd also like to say, though, one bit of thanks, because it's not all us geologists that make our geology happen. There are many other people that contribute. So citizens of Nepal, or the country in which we work, and these can be everybody from the porters who carry our load, or the drivers who drive us around, the helicopter pilots or plane pilots, or whoever flies us where we need to go. And I want to acknowledge them as well for what they've done. One is for international collaboration. And so I ask, why international collaboration or cross-cultural collaboration, to be a little bit more complete? Well, geology problems are complex, and they take many different perspectives, and we all need to contribute. We all bring something different to the table. And while I feel like I've recognized this for some years, I currently have Native American graduate student back in Montana in the United States, American Indian, as you may know them, Native American. And very often she says to me, "Mary, what you just said, that's so Western." So I think about it a little bit, and well, yes, she's probably right. And she says this to me often. She comes from Montana. Her ancestors have lived there for generations. But when they approach a scientific problem, they come in with a different perspective. And I think this is important for all of us to recognize, that to solve these complex problems, we need all of us at the table to bring our perspectives to come to the conclusions that we can. So why a multidisciplinary approach? Well, again, I say geology problems are complex. and we can't just solve them with one technique. So we need to have multiple disciplinary views as well to bring to the table to solve these issues. So I list here a few of my favorite. It's not an exhaustive list either. There are many others. But I will look at a few problems on faults here in the Himalaya, and we'll walk our way through utilizing a few of these approaches to get at the answers to our questions. So, then you say, why faults? Well, I think faults are responsible for a lot of the mountain building that we see. They're responsible for the deformation, much of the deformation of our Earth's crust. And as you all well know here, they present a direct hazard when they're active in terms of earthquakes. They also provide an indirect hazard, whether they're active or they've been active in the past in terms of landslides and mass movements in particular. So what I want to do today is just present a brief Himalayan overview and then look at a few applications of these subdisciplines to work on faults. And again, I'm going to talk about some work that I was involved in decades ago, as well as some more recent work in eastern Nepal. We are at the boundary between the Indian subcontinent and the Tibetan plateau. And of course, as we heard earlier, this collision took place 50 to 60 million years ago with the collision, with the collision of India, the Indian subcontinent with the Asian continent. And the Himalaya, as we know it today, has gained its elevation and its structure by the slicing or imbrication of pieces of the Indian subcontinent in this collisional process. So these pieces of continental rocks are bound by the major thrust faults that we know, the main frontal thrust, which emplaces the unmetamorphosed rocks over the foreland, the main boundary thrust that brings green schist facies rocks up over the sub-Himalaya, the main central thrust that brings our deeper, higher grade amphibolite facies rocks over the lesser Himalayan green schist rocks. And then we've got the South Tibetan detachment system, which is an extensional fault in this contractional origin. And when we present a map something like this. This is from a Najman et al. Paper, but it looks very similar to the ones we're all familiar with going back to Ganser's work. And on these maps that we present, we see these major faults running parallel to the range. And they each have their own unique characteristics. And what I want to focus on to start with is the main central thrust, a passion of mine. And we'll take a look at one of the questions that's been plaguing us, and I'd say in some ways maybe isn't completely solved, but goes back to, again, some of the days of Ganser and other early workers who recognized the inverted metamorphism. So let's take a look at a fault problem and begin to apply some other methods to understanding it. So Nima Rinza Sherpa is going to take us to eastern Nepal. To eastern Nepal, over in the Everest region. And so the map on the right here is a very generalized map of that area, the Dud Kosi Valley coming down from Namche, Everest up here in the northeast corner of this map. Somewhere there's a scale here, 5 kilometers. The brightly colored area down here, so multiple colors, that is what I would call the main central thrust zone. Now, we all probably have our favorite definition of the main central thrust zone. It doesn't matter for the purposes of my talk here, so put in your mind your own favorite view. But the reality is we do recognize within this zone inverted metamorphism, higher grade rocks over lower grade rocks. The rocks within the zone in this area are largely north or northeast dipping. And again, they're imbricates or slices of different lithologies. So the colors here are meant to show different lithologies. The red at the top are the Luca granites of the higher Himalaya. So this is the greater Himalayan sequence here in the light blue color. So the first approach that we're going to use or we're going to apply would be quantitative metamorphic petrology. And I'm going to give you a bit of an old-fashioned view because I'm presenting data from the 1980s. But by using quantitative approaches, we can understand just how inverted is this inverted metamorphism. And so we use different metamorphic reactions, so the equilibria between different mineral phases. And what I've presented here, and I say that this is circa 1988, because that's sort of when this work was done, and we've got a temperature dependent reaction here that's iron and magnesium exchange between garnet and biotite. The other three reactions involve a variety of minerals, and those are all pressure sensitive reactions. And we would apply those to samples from this zone. So again, that general map is over on the right-hand side, and there's a cross-section line here, AA prime, that's shown down at the bottom. So north is at the right-hand side of this cross-section. And what I did back in the day was to sample along that cross-section as well as parallel valleys in the Hinku and the Hongu valleys, and I projected all that data back onto this cross-section with respect to the kyanite isograd. So this K here is the kyanite isograd. It's in the bottom, about the bottom third of the main central thrust zone. So when we take a look at that data, these are two plots. So the top is temperature, bottom pressure. They're plotted with distance on the x-axis. So distance from the kyanite isograd. So again, the kyanite isograd's at the top of the bottom third of the MCT zone. So north, or the samples from the north, are over on the right-hand side, south is on the left-hand side. Excuse that this is in degrees Kelvin. This was once upon a time for a journal that insisted on SI units, and Kelvin's technically the SI unit. But again, the important point is the trend that we do see increasing temperatures when we go up that inverted metamorphism. The pressure data is not quite so clear. And at the time that I did my dissertation, I made the interpretation it was a decreasing trend in pressure, but I will say that I think that that's, if you take away a couple of low points out here outside the MCT zone, it's not quite so clear. But at the time of that work, I interpreted this data to agree with the model that was proposed by Patrick Lefort, some of you may remember, in 1975. And this was a model of placing a hot slab over a cold slab and having metamorphism follow the deformation. So that's this image, oops, this image at the top of the screen here. A few years later, I spent more time looking at deformation fabrics, and I went back to these samples. And then I realized that a lot of the metamorphic minerals are actually overprinted by the deformation, and I changed my interpretation, and I would say now that we had metamorphism predating much of that deformation. So there's an example of applying metamorphic petrology, quantitative metamorphic petrology, to a fault problem in the Himalaya. Okay, but maybe more near and dear to my heart these days is structural analysis. And I haven't really mentioned mapping, and I don't have a slide for mapping, but I will say that mapping the rocks is probably the most important piece, that really gives us the picture with which we can hang all these other methods. But within structural analysis, we can also do kinematics. So that's the study of movement sense. So what's the direction of movement that these faults took? And so this can be scale independent. We can do this at a thin section scale. We can do it at an outcrop scale like I've showed here in this photo, and sometimes even from a satellite image or something a bit more remote. So this is an Augen gneiss taken from the MCT zone near Caracola, if you know where that is, on the Dudkosi River, kind of the lower part of the MCT zone. And the south side is on the right here. We're looking east in this image, so it's a top to the right-hand sense of shear. Okay, other aspects of structural work. So this is not my own work, but there are many people these days doing balanced cross-section work. So reconstructing the cross-sections. And while I personally have some issues with this because we know that there is significant amounts of internal deformation within each of these pieces, it makes it a little bit hard to unfault the faults and take them apart. But the workers who do this would argue that this does at least give us a minimum of displacement. And it's important to know how much shortening we've had or how much movement or displacement we've had on a fault. So another method that we can apply. Okay, next, geochronology and thermochronology. So geochronology, we often date minerals and try to get their crystallization ages, like dating the leucogranites. But I'm talking about faults, so I'm going to look at thermochronology, which I think of then as more looking at cooling ages and trying to understand exhumation. So how did these rocks work their way from the depths that they were buried when they were metamorphosed or maybe deformed up to the surface where we see them today. So the work that I've got here on the right-hand side are plots of ages from 4 locations. Back to this map again, the main central thrust zone, a little village called Gat, a place called Nga, and I call this Ngozumba, but I'm not sure I'm pronouncing that right. The important takeaway, well, I will just say Gat's a really unique one because it's quite young. But I'm going to say the important takeaway on this slide and at the time that this work was done was the main central thrust sample, in particular hornblende. So hornblende has a closure temperature of about 520 degrees or so, and then also looked at the micas, muscovite, biotite, potassium feldspar, and these are uranium, thorium, helium ages at a much lower closure temperature. But the hornblende, 520 degrees, was about the temperature that was determined using the quantitative thermobarometry of about 520 degrees, saying that's when metamorphism happened, which we've interpreted to be just predating the deformation. So this age gave us a close approximation of the timing of deformation of the MCT at about 22 million years. Okay, so speaking of modeling, again, this is not my work, and this is a figure from Webb et al., and he's summarizing work of a variety of different people, different interpretations, but this is large-scale modeling of the Earth's crust. So again, this is yet another approach. It requires a bunch of assumptions. It's quite controversial, but yet it's another way to help us understand what's possible and how our crust might have deformed. Okay, metamorphic discontinuities. Well, we have a speaker tomorrow. I don't know if you're going to speak about, I'm looking at Rodo Carosi here, who's done a lot of work on discontinuities. So he may give us more detail. I'm just going to give a simple example and just make a point. So our initial interpretation, our collective, going back again to Ganser and others, but was we've got the MCT, and then later we recognized the South Tibetan Detachment cutting the top of Everest, and then we just have rocks in between, and we sort of color them all light blue in this case, and we say that's the Greater Himalayan sequence. Well, as we've all spent more time in some of these sort of what we said were homogeneous blocks of rocks, the truth is, no, they're not homogeneous, and there's much more to the story. And I think it was last year when I was here, I did present, I'm sure you remember all the details, I don't, but all the details of that presentation, but in an area just north of Namche, we found a small fault that cuts older fabric. The older fabric represents a thrusting fabric. The younger fabric on the shear zone is an extensional or a normal fault fabric. So again, it's important to go into these areas where we think we've got a homogeneous sequence and look more closely, and when we look more closely, we find new things. And of course, the Himalaya presents a challenge to all of us, I'd say, to find these things, because we've got very rugged terrain, we have vegetation, we have landslide and moraine deposits and glaciers and lakes and other things that cover up the really good rocks. So it's something, it's job security, and it gives our students something to work on in the future as well. So, okay, geomorphology. I'm not going to say a whole lot about geomorphology, but it's important too, and it's the landscape. And in a way, it's probably what attracted a lot of us to geology, whether we knew it or not. And what I've got in this slide is a structure that I'm working on now. This is again the Dudkosi River. Namche would be just off the slide up to the top, flying into Lukla down here somewhere on the floor, coming up that Dudkosi Valley. But about a year ago, I recognized this lineament. It's a topographic feature that then led me and a student and Ananta co-workers to go find this and see that there are indeed fault fabrics that follow this linear trend. There are many other things that we can do with geomorphology in a quantitative way. So I've got colleagues who've taken a look at this and are interested in looking at stream profiles to see if there are nick points in the slope of the streams to find the faults where we maybe don't see them in other ways. Okay, so earlier I showed a map of that was sort of Ganser's original map that had our favorite faults, the MCT, MBT, MFT, and the South Tibetan Detachment. But there are many other faults that go in opposite, or are orthogonal to those structures. And I like this map because it does show the extensional faults that cut across Tibet. And now there are a number of us, and we'll hear some more about this tomorrow as well, of faults that cut across the range. So we're going to take a look at some examples. Okay, so here are the faults in Tibet. Here's some of the faults that actually break through from Tibet and cross the Himalaya itself. And here are a few of them by name. And so I'm going to just summarize. Today I'll mention the Yamuna and Ganga fault that have been worked on by Malay Mukal, who's here in the audience and will speak tomorrow, and his students and co-workers. The Takala Graben, many of us are familiar with that. This dashed line here is the Western Nepal fault system that's been fairly recently recognized, is somewhat of a continuation of the Karakoram fault. There's some faults in the Kathmandu Valley. The Benkar fault is what we're calling this fault along the Dud Kosi, and we'll talk a little bit more about that in just a minute. And then again, Malay Mukal has worked on the Kosi and the Gish faults, as well as other workers on the eastern part, so this is Sikkim. Then there are a few faults. Again, many of these are extensional, like the faults we see in Tibet, the Amadreem and the Yadang fault here. So we're going to go first to eastern Nepal, the eastern Himalaya, and take a look where the Yamuna and Ganga faults are. So these are some of the maps that Malay Mukal and others have worked on, or the faults. So the Yamuna is here, if you can see that, and the Ganga fault. Where they're working on faults, they're cutting the main frontal thrust, basically. So they're cutting young sediments, and they've got evidence of gouge. These are active structures. The displacement here, Yamuna about 20 kilometers, the Ganga about 11. We're going to go now and look at the Benkar fault, and that's up in the greater Himalayan sequence, and we don't have evidence to say that it's active, but it seems to be on trend with many of these faults, or have a similar trend to many of these other faults that have been mapped closer to the foreland. Okay, animation. So moving east to the Benkar fault here again on the Dud Kosi Valley. And so I've had a student working on this, Neil Seifert. He wasn't able to make it. He's just finishing a master's. He spent 2 field seasons in this area, working alongside Ananta Prasad Gajarel and myself. And this is his map, and I don't expect you to read the details. I'll just point out kind of the main features here. So again, for the sake of geography, Lukla down here where one might fly into, walking up the Dud Kosi, Namche Bazaar here, the Khumbu Glacier that goes up, wraps around the summit of Everest in this region here. So these colors up in here represent sort of the South Tibetan Detachment area. These come from the map of Mike Searle, some of you are familiar with. The pink lines are the bounds of this zone that we found. And what we see in this area is a northeast striking, southeast dipping fault fabric. It cuts across the other structures. It cuts across the fabric that's more closely related to the main central thrust, which would be down here just south of Lukla. We find on the edges a normal sense of shear, so extensional, and in the core of the zone, we seem to find much more dextral displacement. So we'll look at a couple samples. Looking first on the right-hand side. So these 2 slides are from the same outcrop, and this is looking at the fault plane with a fairly down-dip lineation. And again, I'm sure in the back it's hard to see, but there's an older fabric here that's got some drag coming into this shear zone, a non-penetrative shear zone that cuts this with a normal sense of shear. When we look in the core of the zone, we see a lot of the displacements taking place along sillimanite-rich plains, and it's got a dextral sense of shear. Taking a look at the zone itself, this photograph is taken from the Tengboche monastery area, if you've been up in the valley. Looking to the northeast, And the fabric here is parallel to that yellow arrow, and you can see, get a sense of a bit of the width of that zone. Okay, geophysics, another important method to apply to our fault problems. And there's probably folks in this room who are responsible for this data that's on the right-hand side. But I guess what I like about this plot is that there's a bit of a linear trend. And when I first saw this data, I saw it on a map that was a much larger map, and I knew it was in eastern Nepal. I couldn't tell exactly, and I wondered if it coincided with our Bankar Fault. Turns out it does not. So the Bankar Fault would be over here in the Dudkosi Valley, and it's 2 valleys over, more like in the Hangu Valley. But the important point is that we need to bring our geophysics together with our field studies and our other methods to try to understand these systems. So one of the things about these cross faults, so the Bankar Fault, other faults, is that there hasn't been a lot of work really focused on them. And so what is the importance of them? How do they relate to the Himalaya, to understanding the origin? And I don't have the answer to that, so just a number of the possibilities that we throw around and talk about that might be or might not be, but possibly they bound areas of active seismicity. So you have an earthquake rupture, doesn't go on forever. Is it truncated by a cross fault with some strike slip movement? So that would basically be a tear fault. Or are there lateral ramps underneath this system? So this is not my work, Hubbard, I have a disclaimer, that's Judith Hubbard, another Hubbard, who's a geophysicist. But are there lateral ramps under the Lesser Himalaya or at depth? And are these cross faults the edges of some of the lateral or the duplex structures, sorry, or are they lateral ramps? So these could be one and the same. Maybe these faults are actually continuations of the extension. So if you're stretching Tibet, it kind of makes sense that some of those faults that accommodate that extension would show up down to the south. It's also been proposed that there's rotation of blocks during the thrusting, so maybe they accommodate rotation of smaller blocks, or sneak preview, or maybe deep crustal structures in the Indian continent basement that have been essentially subducted and are underneath the Himalaya, causing some disruption. So a number of possibilities. Well, let me then just conclude and just say that in order to understand faults and shear zones, we need to apply a number of different disciplines to get all the answers that we seek. So through these disciplines, we can locate where the faults are, what their sense of movement was, how much displacement they had, and when they were active. And we'll reach our greatest understanding of these structures when not only do we apply these multiple disciplines, but we all bring our different perspectives to the table and work together on these problems. So thank you.
For your eloquent presentation, and although I think Mary is an American citizen, but most of her intellectual actually life is in Nepal, and she has contributed significantly, particularly in generating knowledge, particularly in this field in the Himalayas. Let us give a big hand to Mary, Professor Mary. And I would like to invite Professor Mary in dash.
Japan side, PI, Nodding Satraps project. This slide shows the importance of basin structures, actually 3D velocity structure of a sedimentary basin. Sediments filling a basin amplify ground motions, and their velocity structure complicates the propagation of seismic waves. The structure of a basin is very important for seismic hazards. This left figure shows you in the intensity distribution due to 1934 Nepal-Bihar earthquake compiled by Dr. Martin and others in 2015. You can see, this rectangle shows you the source fault of this earthquake, and you can see amplification by Kathmandu Valley this slide shows. And the right-hand side figure shows you the intensity distribution due to the previous Gorga earthquake. For this case, amplification not so clear because rupture directivity effect is stronger than that, but I think we still can see some effects of the Kathmandu Valley on seismic intensities. So, in this talk, I would like to compare Japan case and the case here. In other words, we compare now Kathmandu Valley and the Kanto Basin in Japan. The Kanto Basin, or it is also called the Kanto Plain, is a large sedimentary basin in the central part of Japanese main island. Tokyo, the capital city of Japan, is located in this basin, and it constitutes the Tokyo metropolitan area with 4 surrounding prefectures. In Japan, a district is called a prefecture: Chiba, Ibaraki, Saitama, and Kanagawa. The TMA, Tokyo metropolitan area, has more than 35 million people. That is nearly 30% of the nation population. Considered part of the political and economic functions in Japan are concentrated in this area. This area is situated in seismically active region because we have 4 plates related to Japan. One is a Pacific plate, the other is a Philippine Sea plate, and the Eurasian plate, and North American plate come to Japan through Kamchatka and Hokkaido and others. So we have, again, many plate boundaries. Plate boundaries are generating big earthquakes to Japan. Now, I would like to say about Kathmandu Valley. Kathmandu Valley is covered by the districts of, as you know well, Kathmandu, Lalitpur, and Bhaktapur, whose population are 1,744,000 and 468,000 and 304,000, respectively, according to the 2011 nation census. They form the Kathmandu metropolitan area. I will call that shortly KMA, with total population. Some of these figures, so 2,570,000. That is about 10% of nation population of 26 million people. Again, consider part of the political and economic function in Nepal are concentrated in this area. KMA is also situated in seismically active region, as you already know well, the collision between the Indian plate and the Eurasian plate. So I go back to the Kanto Basin. According to the many motivations I already mentioned to you, Kanto Basin is one of the best observed and explored basin in the world, I think. Left figure shows you distribution of strong motion seismometers and the seismic intensity meters. Seismic intensity meters are strong motion instrument with facility of the calculating seismic intensity. Recently, we also deploy seismometers of a continuous observation like this. And Kanto Basin is one of the best explored, I think, in the world. Left figure shows you survey lines of reflection surveys using the dynamites or other explosive. And left figure shows you the distribution of the gravity surveys. And left figures are reflection survey lines and the deep boreholes digged up to the seismic basement. And the left figure shows you the distribution of microtremor survey sites. Utilizing these various kind of data sets, we already established standard procedure of modeling 3D velocity structures using these various data sets. I think that this is very small, but steps 1 to 3, we organize the geological information and gravity survey results. So we construct initial velocity models for the Kanto Basin. We construct a 4-layer model, and we already given lateral variation of the velocity basement. And we then carried out, according to the steps of 4 to 5 of the standard procedure, we carried out joint inversion of the refraction and gravity data like this. This slide shows you resultant depth distribution in kilometer of the second. And second means interface between the first and, second and the third layers. And this shows that of the third interface. So between the third layer and the basement. Finally, according to steps 6 to 7, we made the ground motion simulations, and we did some adjustment for the velocity structure to fit simulated ground motion to observed ground motion, showing like this. Right figure shows you the comparison of simulated ground motions and observed ground motions. Comparison is not excellent, but I think I hope you can think the agreement is favorable. So, our project, which is called NARDEM, Nepal Earthquake Research and Disaster Mitigation Project, Nepal side, led by Dr. Sapkota of DMG, to apply the standard procedure to the Kathmandu Valley. Our project is being collected many exploration studies 4 or 5 years from 2016. This project is supported by a Science and Technology Research Partnership for Sustainable Development of, as you know, JICA, and JST means Japan Science Technology Agency. So first 3 years, we did compilation of past strong motion records, including those of the Gold Coast earthquake, and the compilation of geological information. And we are observing strong motion, strong ground motion from medium-sized or small-sized earthquakes. And last year we carried gravity surveys and the microtremor surveys. Just now we are conducting the reflection surveys. This is an example of the compilation of geological information. This is a cross-section 2D velocity structure made by Professor Sakai of Kyoto University. And this is a surface geology map developed by DMG. And we also compiled cross-section velocity structure, including the bore for exploration, and they are carried out risk assessment project of JICA. And these are strong motion observation sites. Before our project, we have these slow motion stations in the center of the basin, a valley, a blue triangle operated by Hokkaido University, and the white triangle operated by USGS, and green triangle operated by DMG. But surrounding these, we deployed these red triangle stations. There are nine strong motion stations, and inside we have 7 inside stations, and we have two hard rock site stations, circumstance of the Kathmandu Valley. And last year we carried out gravity survey using this instrument, and we already estimate preliminary depth distribution of the basement shown in the larger figures. And we also carried out microtremor surveys last year and this year using the various methods. For example, SPAC method and other CCA method, or seismic interferometry method. Now, reflection surveys being conducted just now in the airport. Reflection survey is done using these vibrator vehicle and observation vehicle and observation cables. Vibrator vehicle shake the ground using this vibrator plate, and then their vibrations were observed instruments deployed along the observation cable, and they are gathered in this vehicle. Now experiment is being conducted, so I cannot show you the results of the experiment, but I hope some good two-dimensional velocity section of velocity structure. This is survey line in the airport. This line extends from the north to the south, and we hope some extension, but we cannot cross the road at the southernmost part of the airport. So this extension was canceled, but the total length of the reflection line is still 4 kilometers. And we will also carry out a small reflection survey in National Agricultural Research Institute. This is airport survey line, and this is a second small line. And after that, we can show you some results to you.
Thank you, Professor Kazuki. It was excellent presentation, and we can see his devotion actually for our help to make us living still long time for Kathmandu. Professor Kazuki, and I would like to invite you to come into the desk, please.
Yeah, I am Lalu Paudel from Tribhuvan University, Department of Geology. My question is for Mary Hubbard. Mary, you tried to constant the movement along the main central thrust using empty-ball thermochronology. Yeah? But if you check the chemistry, microchemistry of minerals from main central thrust, empty-ball, muscovite, biotite, all these minerals are zoned, and they record multiple history of growth or deformation. So how can you constant the movement using single grain thermochronology? I think we should combine microchemistry and microfabric to precisely constant the movement.
Excellent question, and actually you remind me of something I sort of meant to say. So the work that I presented was kind of state-of-the-art in the 1980s. And what we did was use the rims of minerals for their composition. And we make an assumption that there's an equilibrium of exchange of these elements at that rim. We now know, and back at the time we knew as well, we did use some garnet zoning, but when we look at the zone garnet, so the composition's different in the core of the garnet than the rim, we have to make an assumption. So if we measure the composition of the core, what was it in equilibrium with? And often we're looking for a biotite inclusion, and then we make the assumption, oh, it was in equilibrium with that. Well, we do know that a lot of that exchange happens more readily now, and maybe some of those assumptions weren't quite so good. And I'll, full confession, while that was work I did in my PhD, I have not continued in the lines of the latest, greatest in quantitative thermobarometry. So there are new calibrations of those reactions. And while I think using the same assumptions and new calibrations, it doesn't change the result very much, But there are other methods now that are a little more dynamic and can get more information based on some of the zoning that's there. But yeah, so excellent question, and thank you for bringing that up.
I have a small question about the target of the refraction survey. Whether you would like to get the overburden depth of tape to the background, or you would like to get the velocity of all the layers that you have modeled.
The condition under the airport is good. We can hold up to 1,000 meters from the ground. So in that case, we can reach the basement ground. It's the best case, but if noises, experiment is carried out at midnight, so we hope noises are not so great. But in bad cases, maybe several hundred meters or so.
So in that case, what was the length of the array?
Extent?
The length of the array from the source by the base to the last geopole. What was the length?
4 kilometers.
4 kilometers.
4 kilometers.
The energy was enough to reach 4 kilometers from my process. I think it is okay.
I think so. According to now oil person carried out maybe.
In the surveys, have you found faults in the basin with the geophysical data?
Not yet, but we can.
Okay. I think I felt one on the runway when we landed the other day.
I don't expect such a happy situation.
I have actually two questions to Professor Mary. Well, in the case of climate change, actually, how can you see the impacts of climate change on geological structure of the Himalayas?
That's a big question, but actually I think our next speaker is going to address that, yes? Maybe a little bit. Is that right? I would say you hold your question for a climate. Yeah.
Well, how can you see Kathmandu within or end of this 21st century? Will we be still here?
According to technical assessments, I think it is better to move hard rock sites. In Nepal, the hard rock sites, you don't have any flat topography. I think the rock sites you cannot build the capital like Kathmandu. My suggestion is to make buildings stronger. It will be fit to large seismic hazards.
Thank you both, the professor, who made a very remarkable and significant contribution to science, geological science, for Nepal and the globe also, because Himalaya is one of the most important area of the world. We are coming to the close of this session. I have to leave in another meeting, so I will be up to here. That is why I have to leave. And I am really thankful to the society, Geological Society of Nepal, and all the scientists and young scientists, my fellow colleagues and university students who are here and very eagerly listening and learning what these two eminent professors actually made the presentation. And all this actually is related to how we Nepali in future will live, particularly Professor Kazuki's, research, his team's research, Tokyo University, which is one of the best university in the world, undertaking the research in Kathmandu Valley, and we are very grateful. We are very proud of this because this is in seismic zone, and let us give a big hand to Professor Kazuki. Similarly, Mary, who actually half of our life is here in Nepal, I think, since long time ago. She has been a great, explorer, admirer, and cultural and anthropologist also, studying there with the human people and bringing people in collaboration, actually, research collaboration for undertaking these, geological events and sites of the Himalayas. And I think this piece of research act will be very, very helpful, not only for Nepal, but also for China, but also for India, Bangladesh, and many neighboring countries. because Himalaya is the common for all of us, extending from Afghanistan all the way to Myanmar. So this research will be a milestone for us, and our young scientists and young students, our sisters and brothers, will continue to actually follow these two research. And let us give a big hand to Mary and thank you, Mary. I am really happy to be here and to chair the sessions, since I will not be able to attend the very, very delightful and very interesting, papers, but I will go through the paper after the proceeding comes. And of course, eminent scientists from India, Bangladesh, China, and other countries are also, Italy, are also here. They will be making a very good presentation, and we are eager, we in National Planning Commission are eager to receiving the best message and summary message, so that we will be able to actually enhance research and development. Because one of my responsibility is to oversee the research and development of Nepal. So therefore, I am very happy. Unfortunately, I will not be for a long time, and my colleague, Madam Singh, will be chairing this following session, I think. She is the co-chair of this session. Let us give a hand to her also. And she will be here. We'll meet again sometimes here, because 2-3 days I think we will be here. So I am really thankful to you, and thank you very much for the organizers. Thank you very much.
But I won't let you go like this. I want to have some token. Thank you, Chair, Honorable Member, National Planning Commission, Dr. Krishna Prasad Wali, for giving his precious time to us and chairing this session. Due to some important schedule, he had to leave. So I would like, on behalf of Nepal Geological Society and 9th Geological Congress, I would like to thank him for chairing this very first sessions efficiently and eloquently. I want our keynote presenters to be presented with some token of love from NGS, and I want Dr. Oli to present token of love to Professor Hoover and Professor Kokutsu. On behalf of Nepal Geological Society and 9th Geological Congress, I would myself like to present a token love to Dr. Krishna Prasad Wali.
Now we move on to in this session we have two inviting lectures. First lecture is given by Professor B.C. Tiwari on the topics global climate change and its impact on the third pole Himalaya, Himalayan tsunami and the geohazards in the Uttarakhand, Himalaya, India.
This is my pleasure to be here again. I was here in 2015, just before the conference was there, just before this earthquake, that is the earthquake, and again I'm here. But you have heard just now about the tectonics of the Himalaya and the major fault thrust system which is affecting the whole subcontinent. But now let us thought about what is going on, the impact of global climate change in the Himalayan cryosphere, that is Hindu Kush, Himalaya, Tibet region. The glaciers are there, that is the cryosphere, and it is now the global warming and the impact of climate change is seen there. All the glaciers in Himalayas are melting very fast, right from the Uttarakhand and JNK to the Sikkim in the east, including Nepal. I will talk about the Uttarakhand Himalaya in the central part, where in 2016 and 17, during the monsoon time, this natural hazard occurred because of the GLOF, that is the glacial lake outburst flood in the Kedarnath shrine. So the lake there was beached by the heavy snowfall there and the western disturbances and the heavy Indian monsoon. Generally this area we don't get monsoon, but that is now the extreme climate change, extreme weather change, that we have heavy rainfall in higher regions also. So this is the Himalaya Karakoram Tibet region, which is now affected by all types of the climate change. So what we are facing in India and Nepal and other parts of the Himalaya also is the gulf, then landslide, then earthquakes and seismogenic landslides. The landslides are occurring after the these greater earthquakes. And we are facing the common problem all along the Himalaya, in this region, and in parts of Karakoram and further in the Tibetan part. So now the disaster, the Himalaya is now described as third pole. We have North Pole, South Pole, permafrost is there, and Himalaya is now considered the third pole. And this third pole research was initiated a few years back from China. So they have now this third pole research, which is generally clubbed with the Himalaya Karakoram Tibet workshops. In India, we had it. In Germany, every next year we have these meetings are there. So we are now combining what is happening in the HKT region and how the third pole is getting shaped because of the climate. So the Indian subcontinent is the world's most disaster-affected area, since it lies in the Indian plate, which is still moving northward anti-clockwise, and major earthquakes are occurring because of the subduction process. Professor Koze has just now shown you the model of the Himalaya. So the 60% of the Himalaya are lying in the high seismic zone map of the country. The disasters, that landslides may also be triggered by seismogenic processes and further can cause the loft, that is landslide, lake outburst flood. And the recent climate change and the meteorological extreme conditions have further increased the natural calamities like gulf and cloudburst. Is very common now in the Himalaya from Ladakh northwest to Sikkim in the northeast. These are the glaciers. The satellite map clearly shows that they are retreating very fast. This is Gangotri Glacier. So these pictures clearly show there is a shift in the snout from last 20, 30, 40 years. So there is a drastic shift in the glaciers. This map also shows that right from accepting part of Karakoram, this part is highly affected and the rate of glacier retreat is very fast. So if we look at just the all mountain systems, so the Himalayan glaciers, they are, you can see in 1920 in Everest. So this is 1929, 2008 and now. So you can see how much snow has been melted there. Then the other earthquakes, other parts of the world also, then you have in Europe and other areas also. So the meltdown is there. Everywhere this impact of climate change is there. This is one example from India again, the Tipra Glacier. So it has been studied in 2008 and 10, and this is the previous history here since 1960. GSI has worked there, then our institution has worked there. So this is also showing this ice mass up to level in this Garhwal, it is very shrinking very fast. In fact, I was in Wadi Institute of Himalayan Geology in Dehradun. After my superannuation, I joined Sikkim University in Gangtok. So all of this work was done during my tenure in Wadi Institute, where the glaciology and geotechnical group scientists were working with me. Then coming to the basic thing about the Earth climate system, this consists of the 6 major interacting subsystems, the lithosphere, then we have the atmosphere, and then hydrosphere and cryosphere. So now our these studies are confined to the cryosphere only. And biosphere, of course, because the cryosphere, biosphere, all this is affected by the recent climate change. And the solar radiation also, because that cannot be ignored. The impact of solar radiation is there. And the anthroposphere. That is the recent, Anthropocene is now new geological time scale. So that also shows that how much anthropogenic effects are there besides the geological impacts. So this example, now confining to the glaciers. So the Indian Himalayan region is home to about 7,000 glaciers covering an area of about 8,500 kilometers. They play crucial role in the shaping and influencing the environmental conditions and climate change in India. And Himalayan glaciers are the ticking time bombs, because what I've been going to show happened in Kedarnath Shrine is also going to happen like Lonak in North Sikkim. So all these high altitude lakes are going to behave in the same manner what happened in Uttarakhand. So we have to take care of these high altitude lakes. Like this one. This is a very common example of the high altitude glacial lakes in the Himalaya. And if we go by the monsoon, Indian summer monsoon, because that is now affecting this in high Himalayas. So we have this monsoon precipitation in the Himalaya during June to September. That is, the moisture from Indian Ocean comes here, and the rising air is there. It is not allowed to cross the Tibetan Plateau, does not allow it to cross, so it precipitates there. So that is the thing, we get the ISM. And now this is the IPCC recommendations and observations that there is increase in the annual mean temperature is rising. Then the increase in rainfall and its erratic behavior causing floods and droughts. So that is, we are now experiencing these frequent erratic behavior and heavy this precipitation. Then increase in the sea level due to the thermal expansion, melting of glaciers and ice caps. So it is all happening. This is the Uttarakhand region. This is the Kedarnath Shrine here. And the Chorabari Glacier is here. And this is the companion glacier. And Chorabari, this lake is there. So it happened in June 16-17, 2013, the breakup of this Chorabari lake, and a disaster happened that killed more than 10,000 people in just 2 minutes. And that is the most recorded disaster in the world, where suddenly, this is a very important event. So the rainfall was there in the June 15-16. It was not expected because of the western disturbances. This rainfall was there, and Indian summer monsoon was already heading. So this is the Chorabari glacier here, and this is the temple, and then these are the glaciers. So Kedar peak is here, the highest peak. Then we have these glaciers. Then these clouds formed, and then started heavy rain. And this is happening right now in other places also. So after that, this was a heavy rainfall that never happened there before. So after this rain, this was the Chorabari Glacier Lake, which started filling up. So its dimension is 300 cross 200 cross 17. Lake area is 60,000 square meter. Lake volume is 102,000 square meter, and this much water is there. So slowly it was filled up, and then it started filling up. it never happened before. Then it started breaching. So lake burst. Our team was there at that time. It was working, and then they moved towards the lower altitude. So the pressure released from here, and finally the lake burst was there. And this is actually recorded in time because we had all the instruments there. It was recorded. So that happened, and you can see after that what happened is because this was the peak time for the pilgrimage, most of the people were going there, and there was no warning from the meteorology department. Nobody knew it is going to happen. Absolutely no idea that how these 10,000 people are going to survive there. Most of them were killed. So this was the before flood and after flood. Then two events occurred there. The heavy rainfall and rapid melting of the snow ice during 15 to 17 June, and then that has resulted into two flash floods, event in the Mandakini River. An event one was on the June 5:15 p.m. Due to the torrential rains, flood in the Mandakini, Saraswati River, then Madhuganga and Dudganga, these catchments there, resulting in excessive flows across all of the channels. Some of the channels were dried and they were reactivated. An event to happen, the continuous heavy rainfall and rapid snow ice melt caused expansion and overflow of this moraine dam, Chorawari Lake, which collapsed on 17 June in the early morning. So that was the phenomena. This was already recorded from Nepal earlier also. So this was much bigger, and so that was the gulf which resulted in this calamity in this region. And then there are studies not only in the Garhwal Himalaya, but all along the Himalaya, right from Ladakh also. These events were continuously recorded after 13, 14, 15, 16, and now in Sikkim also we are doing it. So that is the thing, you can say the impact of climate change and the melting of glacier and the extreme rains. So this was the Chorawari Glacier, the lake burst, and then the temple was here. So all these rivers were overflooded, and downstream it was disastrous. Like why the name tsunami was given? Because it is like the Japanese tsunami, where everything was, blown with the. So like here also, you will see some pictures also. Everything was the rivers were swollen, and it devastated all the bridges, all the buildings, everything. So this is the view route to that, and then a lot of landslides occurred, and all these people were perished. This is just scenario at the time of this disaster. You can see the river is flowing here through the temple. So this is the Chorawari Glacier burst. So again, the landslides triggered, and there are 500 new landslides were triggered in this region, all along the Alaknanda and Bhagirathi rivers. So this is the region here, Kedarnath, then this Mandakini river, then Alaknanda is coming from this side, and Bhagirathi is coming from this side. So the disaster was more in this region, in the southern region, because all water was going down. So more casualties and damage was in the southern part. This is just geological map showing this is located in the higher Himalayan crystalline, Badrinath granite, Kedarnath granite, just in MCT zone. All these faults are first mapped, and so they are reactivated, most of them. These faults were reactivated. Then this paper was presented just after that. The HKT was in Tübingen in Germany, where I also participated and presented the first report from this region. So the first this type of event. Then what were the causes for that? So we had the interaction of easterly and westerly systems of the rains, because before that the westerly system was not affecting the Indian monsoon. This time, according to meteorologists, the Indian this monsoon and westerly events, they were together simultaneously. So the low pressure areas developed and they embedded these mesoscale systems. Then the orography of the region plays a dominant role by increasing the convection, and hence the intensity of rainfall increased. Sorry. So this happened actually. This was the westerly disturbance, and then the Indian summer monsoon was adding. So this caused a low pressure area in this Kedarnath region, and this heavy precipitation was there. Then this was proposed after that to detect that the Doppler radars the system may be put up there, or some early warning system may be developed to at least, because it's difficult to put the Doppler radar at such high altitude, and according to meteorologists it is not possible. They have to do it at the lesser height. So, but it was done after that, and then to detect these extreme weather systems, monitoring of these heavy rains, and then the more use of the meteorology and for the disaster risk reduction. Then, because of its geography and topography, India has faced serious large-scale natural disasters in the past, and this area is also affected by the major earthquakes. Chamoli, Uttarkashi, all these greater earthquakes have occurred there along the MCT. So this is a highly active area in seismic zone 5. So the available statistics show that the number of disasters as per year is increasing, but also the number of people affected and killed is also rising. So this is the Kedarnath shrine, and this is just now a few days back. So there is again heavy snowfall now in entire northern India. All Himalaya is now getting heavy snowfall. So there is also, it is in November early. This has started very early. It has been generally in the month of December, January we get this snow. And these doors are closed for the pilgrimage. Then the National Monsoon Mission was established to study the extreme rain events, to study the summer southwest monsoon. And the variability, onset, withdrawal, and the quantum of rainfall can greatly influence agriculture, economy, water resources, power generation, and ecosystem. Then the predicting extreme events like extreme rainfall in Uttarakhand in June 2013 and other regions of the Himalaya, and recent floods in entire this central West India are future aspirations of these. So what is happening now? This again the erratic monsoon. The entire northern India is flooded during this monsoon. Even the deserts were affected by Rajasthan desert, and all along this. The entire northern India has received a lot of heavy rainfall, excessive, that is again not normal. Then the disaster management planning has been done in the context of this climate change and the establishment of appropriate these institutional mechanisms at the state, district, block and gram panchayat level for managing the risk associated with the projected enhanced intensity of the disasters, such as land floods due to high intensity of rains, bursting of these hydropower dams due to both extreme rainfall and blocks. So further, it is essential to install early warning systems and associated hardware, undertake remote real-time monitoring and automatic data transmission, undertake the hazard mapping of these key watershed areas and implementation of the evacuation plan. So already this has been established and this work is being done. Then since this is a common problem in the all the Himalayan countries, so what we need to develop is the integrated efforts between the mountain meteorologists, landslide experts, flood and disaster management experts will provide a platform for multidisciplinary systematic scientific program and guidelines to handle such disasters and develop comprehensive integrated plan of the action and early warning system for the Himalayan mountain system. So these are some of the landslides which occurred just after this disaster, and they are in different climatic zones. We have from sub-Himalaya and the lesser Himalaya, the central and higher Himalayas. So all parts are affected by this. Then this is that the landslide monitoring system established for the early warning system. So that is also being done in Sikkim. So that will help us to do some early warning system for landslides. So the future implications are the paleoclimate research gives us a much longer perspective to evaluate our understanding of the climate system and how it might change in future. So Himalaya is highly sensitive to the climate change, and interdisciplinary approach is now required for the climate study involving climatologists, meteorologists, oceanographers, geologists, botanists, chemists, glaciologists and climate models, because as done in Nepal, we have to do the bioengineering also. That is very successful in Nepal. So in parts of Himalaya in India also, the bioengineering is now being applied to stabilize the slopes. So how much time I have? I have some time. Because now the general problems, these are the what is happening on other mountains. So this is, you can see the effect of global warming here. Then Alaska, see 1914, 2004.
I would like to interrupt you that you have 5 minutes left.
5 minutes, okay. So my main topic is covered already. These are some general pictures for other mountain systems. What is that? Because it's global problem. So 80% of the glaciers are melting, and now the drastic increase in the frequency of extreme events, wildfires. Now, see, from Australia to Los Angeles, everywhere there is fire. It is in Europe, it is in India in summer, in all the Himalaya forest fire. Now it is in USA. So everywhere we have now the forest fire. And that is, of course, contributing to the more carbon dioxide in the atmosphere. So this is a global event now. Fires are there everywhere. And of course, the volcanic activity. Recently in Southeast Asia, you had Indonesia, a lot of this volcanic activity, then tsunami was generated. So these are the geological as well as the anthropogenic causes. Long back it was already warned that the sea levels are rising, increase in the extreme weather occurrences, they're like hurricanes, tornadoes, flash floods, tsunamis, then increase in the occurrence of the fires, and increase in droughts, melting of polar ice, that is everywhere, Antarctica, Arctic and Himalaya. Just finishing this one. Melting of the polar ice caps, including Himalaya, then greater variation in the fluctuation of temperature, rising sea level, everywhere it is there, an increase in the extreme weather occurrences, that is cloudburst happening in Himalaya, heat waves happening in India and other places, hurricanes, tornado, everywhere, then glof in Himalayas, very frequent now, and flash floods, and then the tsunamis. So these are the, this is happening. An increase in the occurrence of fires, it is already going on. An increase in the droughts. Recently, in India, Meghalaya, this Meghalayan new geological age is established based on this Paleocene research in this Anthropocene. So, and the latest, the geological time scale is Meghalayan, that is 4,200 years. when the drought was there. It is already recorded, and this is a new geological time in Anthropocene. Then climate change is causing more than just warmer oceans and erratic weather that we are feeling now. It also has the capacity to alter the shape of the planet. So this is affecting all of us about the agriculture, water, energy, transportation, health, infrastructure, economy, and disaster. Because most of the people are living within the South Asian region rather than in other part of the world. So I end here. Thank you very much for your attention.
Thank you, Professor Tiwari, for your significant presentation on the global climate change and its impacts with the living example of the Uttarakhand Kerala that happened to take place in June 15 to 17, 2020. Thank you, Professor Tiwari. Next speaker is Dr. Subodh Dhakal on the topics landslide research in the South Himalaya of the Nepal, collaboration between Nepal government and Tribhuvan University. Please welcome Dr. Subodh Dhakal.
My name is Subodh Dhakal from Tribhuvan University, Department of Geology. A project that is undertaken by Tribhuvan University in collaboration with the President Tarai Malaysia. No, the name is long, so I call it short PCT and CDV. So I may tell you later. So what is that exactly means? So that research was undertaken in 2015, and the second phase was completed last year. So I want to give some brief introductions and results about what we have done and what we achieved in this presentation. So this is the content of my presentation. This is the introduction, problem identification, of project background, working area, objectives, methodology, findings, database and results, and conclusions, implications and collaboration options. So these are some of the headings I'm going to present. To go for the brief introduction about the South Himalaya, in fact in Nepal, South Himalaya is popularly known as Sure area, and Sure area is presently considered as the issue of national pride, because this area is being degraded day by day, and this conservation is very much important to save the life of people and of course the whole ecosystem and the environment. So this is the red portion is almost the Sure area, the South Himalaya of regions. And what is the problem identification? So in the recent years, there are a lot of landslides and soil erosion problem in this area, and these problems are occurred due to the effects of two parallel problems. One is the naturally involved regions, and another one is the human interference or anthropogenic problems. And these are some of the problems of natural phenomena, for example, dynamic landforms, fragile rocks, and intense monsoon rainfall, etc. And in case of the anthropogenic problems, they are weathering and increased surface dynamism, deforestation, overexploitation of construction materials, and those things. So both of these factors are accelerating the landslide phenomena and the erosion process. And because of these processes, the Tarai area, the southern part of Sure area, the Siwaliks, is being flooded and of course sedimented. So it gives a lot of problem in the southern part of the Sure area as well. So this is main problem of this area. So about the project, realizing the lack of applied research in the landslides and surface erosion, PCT and CDV signed the first agreement with Tribhuvan University to undertake the research on landslides of Sure area in August 2015, and the second agreement was signed in September 2016 to conduct landslide research in 12 districts of far western, mid-western and western Nepal. So it is the fund was provided in the form of grant, and with that grant to conduct this research. So these are the working areas. So this is the district names, and you can see the working area in this part. And the second phase is from this part of Nepal. So these are the second phase. So in total, we have completed the 22 districts of Sure area out of 36 districts. So the main goal of this research was to study in detail the landslides of Sure area so as to reduce the disaster risk and support the board to conserve the area. And these are some of the specific objectives: to make the landslide inventory, GIS database and inventory maps, landslide characterization, landslide hazard maps, vulnerability and risk assessment, landslide mitigation prioritization, technical and financial plan for landslide mitigations, dissemination of findings through scientific publications and mass media, and help build national research capacity on sewer resource and conservation. In fact, you see there are a lot of objectives, and of course it has a very wide scope of research, starting from the landslide mapping to the mitigation designs and up to the scientific dissemination, knowledge disseminations, and of course the resource capacity enhancements, capacity building of the resources. So this is the complete package of landslide study, because what happened is before there were a certain level of resource in the landslides, but those studies cover only the part of the these problems, and therefore we want to take the responsibility of whole process. That means from the starting of the landslides to the mitigations and of course the capacity building and those things. So this is the complete package. So this is the overall methodology of the resource. In fact, we have two sides of methodology. One is for the image interpretation and satellite image interpretation, and another one is the field verifications. And by this we identify the landslides, where are there, and spatial distribution of landslides and their size and all those things. And then we make the GIS database of the of every landslide to have delineated from the images and of course from the field data. So we make a complete database of each of these properties or characteristics. And then we make the different causative factor maps for landslides and make hazard maps. And again we undertook the vulnerability assessment and make vulnerability index maps and vulnerability maps, and finally we make the risk maps. And after risk map, we prioritize the landslides so that the government can choose the highest problem landslides to mitigate, because all landslides cannot be mitigated at one time. So this is the our generalized methodology of this study. So if you go to the methodology in detail, so we have the indirect surface data and direct surface data. So indirect surface data, as I told you earlier, so these are the GIS layers and topographic maps from Survey Department, geological map of DMG, and Rapid Eye Imagery 2009 and Google Earth Imagery 2000 to 2015. And for the direct surface data, we collected the geological, engineering geological, geomorphological, and field test data. And of course, for the laboratory, we took direct shear test, unit weight, specific gravity, compressive strength, liquid limit, plastic limit, etc. So these are some of the tests and some of the methods and tools we used in our research. So other tools are ArcGIS, QGIS, and AutoCAD drawing. So these are some of the highlights of the methodology. This is just general features of the study undertaken by the geologist or engineer geologist in the field. So these are the tools we used. And in the field, what we did, we make a checklist, and we fill up that checklist for each of the landslides, and sketch and geometry measurements in the field of each landslides, classification of landslides based on activity and processes, and division into different geotechnical units, and find out the main cause and possible triggers, then sampling of landslide materials, finding tentative mitigation options, and ID-based landslide inventory in GIS, and mitigation prioritizations. And considering the topographical, geotechnical, and social factors, we prioritize the landslides for mitigations. So this is one of the example of the landslide reporting form we call the landslide inventory form we use in the field. Of course, it has many things to collect in the field. So some of the important parameters are sketch geometry profile, classification, division into geotechnical elements, main cause and possible triggers, sampling, assess tentative mitigation options, and mitigation prioritization. Inside the landslide itself, we have collected the information, for example, what is the date of landslide and what is the name of landslide if there is any, because when the government agencies want to work for the mitigation of those landslides, they want the exact location and exact name of the landslides. And of course, the general public also know that name. That's why we use those type of data. And here you can see the landslide type and landslide, what is the landslide is on rock or on soil, and what is the drainage condition, and what is the other triggering factors, and structural controls like fault, fold, what are there, and lithology control, what is the lithological variations over there, and if there are any other comments the researcher can fill up here. So we collected this field data by using this type of landslide reporting form. In addition to this, as I told you before, we collected a sample from each landslide site, and those samples are tested in the geotechnical laboratory of Institute of Engineering, Puchok campus. And after that, we get the dimension, or we get the design, engineer design for the landslide mitigations. So if I talk some of the, if I show some of the results we obtained, or what database we prepare, these are some of the results. For example, we separated the landslide into cluster because there are certain areas which are very close to geographically very close to each other, and other areas are far. So those areas very near to each other we call one cluster, and another cluster and another cluster. Like that we conducted our research, and this is the database we prepare. For example, this is the district name, and what is the district area in Chure, because all districts are not included in the Chure area of Nepal, so that's why these are different. So we make this type of all database for all landslides we studied in our area. So if we go to some of the results, what we prepared, it is the inventory map of landslide. For example, this is one administrative unit we call Makapanpur district. So this is landslide is given in red, yellow or blue color. So that means these different sizes are for different size of landslides. So red landslide, red color means large landslides. Its dimension is greater than 10,000 square meter, and small one is the blue, that is less than 1,000 square meter. So we separate the landslides depending on its size. And of course, this is another example for another district. And what we did is because our topographical map is very old, that is, I think it is prepared mostly for 1994. So 1994 and this time is 2018 or 2017 is very long time. So that topographical maps have not been updated. So what we did is we take the topographical map of the survey department and we prepare the one landslide inventory map over that topographical map. So that topographical map is updated in terms of landslide occurrences and their size. And we prepare the complete database. We have for example, landslide identification number, we saw LDI, landslide identification number, LDN, that consists of 10 digits included, like VDC name, ward number, and landslide number, and geological formations, watershed, longitude, area, and of course the volume of the materials from the landslide, those area in that particular landslides. So again, if you go to the detailed characterizations, there are many more parameters, because for example, if you see landslide name, then location, northing, easting features of landslide, whether that landslide is found in single or that is found in cluster or in number of landslide. For example, basically what we have seen is in the sub-Himalaya region or in the Chure region, landslides are very small, in general very small, but they are very close. Many landslides come together. So we say that is the cluster of landslides. And then area, volume, and which stratigraphical unit, and what is the rock type, orientation, weathering condition, soil type, and river type, soil depth, surface water, groundwater condition, slope angle, slope aspect, land use, and landslide type. So these are all the complete database we have prepared for those studied area. And going to what we found in the causes of landslides. For example, there are different types of causes in Chure area or in the South Himalaya region for the landslides. Number one is, I have prepared one of the photographs I have shown here, that is the structural control of landslide, that is in the contact between the lower Shivalik and the pre-Shivalik. So we find that the geological boundaries are one of the main reasons for occurring the landslides. So it is one of the particular type, and another one of the causes is the lithological causes, and this is in this particular photograph, this is from the lower Shivalik muddy stone, and this muddy stone is highly weathered, and there is phases of erosion, and after erosion intensifies, then landslide occurs. So these are some of the causes. And if you go some other regions, for example, we call it tectonic regions, that is coarse and loose soil at the top of fragile muddy stone. Because of some unconductivity and those things, so some geological phenomena, the landslides are occurring in this area. Of course, another common problem is the reactivation of old landslides. reactivation is natural as well as anthropogenic. For example, in those areas where there is excavation for road construction, there are a lot of reactivation of landslides. And in some particular area, there are some other landslides which are reactivated without the human interference as well.
Dr. Subodh, I would like to proceed to finish in time. You have left 5 minutes.
So, it's 10 minutes only?
5 minutes?
Yes.
Yeah.
So another cause is the poor drainage. Poor drainage is another cause, and another one, of course, I have to make it fast. So it is the undercutting by rivers. I am showing you what are the typical reasons for the causes of landslides in this area. And another is poor drainage, interbreeding of weak and strong rocks, because in sub-Himalayan region there are certain relatively stronger sandstone and monostone interbreeding. So that is why the sandstone bed, competent sandstone bed are slided in the form of rock slide or rock fall. So this is another reason. And of course, fault control and joint control landslides, these are common phases. And if you go to the landslide types, the number one I have shown here is the landslide type is the granular flow. Normally granular flow is not found in any literature as a landslide type. But we have introduced this term because there are a lot of phases with the granular matrix being flowing towards the downslope. So this is from the upper Shivalik region. And another one is the rock slide. Similarly, deep-seated landslides are there. This one is the Godavari riverbank. That is popularly, this Godavari area is popular in newspaper because Godavari is going to be, it's proposed for the headquarters of certain municipality or something like that. So there is some discrepancy over there. And this is the gully erosion with granular flows and those things. And of course, rock fall, as I told you before, and another one is the gully erosion. Similarly, we have used one term called erosion-induced landslides. In fact, there are certain parameters, certain things which are inducing landslides, and this is erosion-induced landslide because the landslide started from the erosion, but after the maximum incision, the slope get fall or slided and take the form of landslides. So another typical phases is the landslide cluster, as I told you before. And what we did, so these are the landslide sketches we have prepared for each and every landslide we have studied. So this is the just one representation. And we didn't only do the database for the administrative boundary, but we did it for the watershed level also. So this complete package of dataset is found for watershed level also. And second component was the landslide hazard mapping. These are some of the factor maps. I cannot go in detail about those factor maps, but I am just showing you what we have done in this project. So this after that we prepared the hazard map like that, and we use statistical bivariate analysis for the hazard mapping. So this is the watershed level, and we distribute the hazard level based on the district and the Gaonpalika, Nagarpalika, that are the local level administrative boundaries, and what percentage of hazard level are in those areas are also given. And another component is landslide volumetry. We use the spatial multi-criteria radiation analysis for this, and basically we use the 4 parameters for volumetry, that is the social, economic, environmental, and physical parameters. And in case of social volumetry, we use the population density, sex ratio, dependency ratio. These are some of the references. And for physical volumetry, we use the housing index, road network, and like that. Economic volumetry, mostly we focus on agricultural land, and environmental volumetry, we use forest area. We consider forest area for determining the volumetry. And then we determine the volumetry index, and finally we make volumetry maps for all those districts and the watershed level. And of course, we have the watershed level database for the volumetry class as well, for all the watershed. And finally, integrating the hazard and volumetry map, we prepare the risk maps. And this is the final output of for categorizing the area into what much of risk factor over here. So this is the risk map we prepared, and again we distribute the risk class depending on the watershed level. And next, our next objective was landslide prioritization, because there are I forgot to mention you, in total nearly 7,000 landslides were mapped in this project. So 7,000 maps. All landslides are not necessary for treatment. They can be treated very simply our local government, and some needs very heavy structures as well. So what we did is we prioritize the landslides depending on the geographical location, geotechnical characteristics, specific landslide risks and elements of risk. These three factors are combined and make the prioritization. And on the basis of three parameters, scores were given to each landslides, and finally high scoring landslides were given high priority for prioritization. And this is the landslide prioritization for one of the district, Donai Dura district. So for example, if you go for Sunkola landslide, okay, I'm going to finish it soon. So for example, if you go for Sunkola landslide, ID D13 is the highest, I would say, highest level in prioritization. Because if government agency want to treat the landslide or mitigate the landslide, they should go for the Sunkola landslide with ID D13. This type of database we have prepared in our study. Landslide mitigation measures, of course, we have principally we have used the low engineering structure. For example, not heavy, light structures, and mostly we focus on, if possible, to the bioengineering options as we have been using in Nepal. These are the, and one more thing I have to say is that this is the photograph of landslide, and we put the design over photograph itself, so that government agencies can easily understand what is to be done in those landslides. So this is the parameters for the landslide mitigation measures. I have very little time, that's why I skip that. And again, what we did is we prioritize the landslide depending on which agency can handle that landslide. For example, we integrated this into three categories. Those landslides which can be treated by communities itself, those landslides which can be done by line agencies, and those landslides which needs external interventions. So these are the categories, and these are the landslide number that we prioritize. So about the capacity building, we have 1 PhD research ongoing and 6 master's theses have been already completed, and fresh graduates have were involved in this project, and researchers participated and presented their papers in the international conference in Kathmandu. So I have to show you in quick. So what is the final output of one of the final output of our research is the landslide atlas. We have prepared for 2 phases. First phase and second phase. We have prepared the landslide atlas with very brief summary and essential elements of those landslides, and of course how can we mitigate that landslide and what is the cost of mitigation of that landslide. So it is given in this landslide volume. So this is one of the output of, and of course this is the, so finally I conclude. So integrated hazard, vulnerability and risk approach can be the complete package of precisely managing the landslide hazard. Main cause of hazard are geological, structural, incomplete rock types and different weathering, poor drainage, river undercutting, and road excavation on all landslides. And rock slide, rock fall, debris slides, earth slides, and complex landslide are most dominant types in this area. Bioengineering is a promising method to mitigate landslide, integrating drainage structures, check dams, retaining structures, and suitable vegetation. And existing land agencies and communities may implement the mitigation plans of many landslides if technical support is provided. So it has some implication for soil conservation, disaster risk reduction. For example, it provided comprehensive database of existing landslides and potential landslide zone. It also provided the methods of controlling landslide at high risk and the costs associated with them for future planning, and provided qualitative data on the potential civil production zone that will support policymakers to decide on construction material dilemma. And it also will help to enhance the capacity of the government land agencies, particularly in district soil conservation. And this is the project team who were involved in this project. And we can have some collaboration. We have some options. For example, we have to collaborate with the universities or high standard research organizations from around the globe to make our work more efficient and applicable. And what are the collaboration options? For example, mapping of landslide in poorly accessible terrain, that is particularly a problem for us, and field testing of rock and soil mass, because we have very ill or not well equipped laboratory, and landslide mitigation techniques. We may go for the technology transfer type of things, and landslide early warning is most important, and capacity building of resources. These are some of the findings and research of this project. So thank you so much for it.
Thank you, Dr. Shiva, for your geological sound. I would like to request Mr. Ramprasad to close the session.
I, on behalf of Nepal Geological Society, would like to thank the presenter, Professor V.C. Tiwari and Dr. Dakal, for their excellent presentation. Nice to see the audience here, the participants quite attentive. So thank you all. before closing this session, I would like the chair, Ms. Shobha Singh, to present a token of love to our presenters. First to Professor V.C. Tiwari, then to Dr. Subodh Dhadwal. He is our co-convener also.
We have 9 papers covering different disciplines. My co-chair is Dr. Diliram Thapa and rapporteurs are Naveen PK and Junu Preti. So the first presenter is Professor V.C. Tiwari.
Afternoon session. So I have to be very fast and completing in 30 minutes. So this lecture is about the India-Asia collision, movement of the Indian plate collision around 55-50 million years back. And then what happened during that time? Three things were there. From the Indian subcontinent, South Asia, we have very good records of the collision. In the northwestern part, in the central zone. In the northeastern part, we have this Myanmar disappearance of the Technicak Ocean. And the Technicak Ocean has, can you come to this? Has very good record of the, we have very good record of the mega events like Deccan volcanism, late Cretaceous Deccan volcanism, then Paleocene thermal event, and at the same time the mass extinction in the ocean and appearance of new life on Earth. So all these events are recorded from the Meghalaya in the northeastern part and some parts of southern India and central India. So these are the sections we have studied globally about the KT boundary. Best sections are in Chicxulub, that is in Yucatan Peninsula, Mexico, where the drill cores are there, and the asteroid hit here. So a lot of data is available there at the KT boundary. Then in India, we have from Meghalaya here, this Umse-Rinko River section, and then some parts of this central India, near Nagpur, and some in Cretaceous, Krishnapalli. Then in European sections, we have mostly from Italy, Denmark, and these sections are very good sections. First studied for the KT boundary mass extinction. Then we got some data from Brazil and then Argentina also. So for the first time, we have generated the mercury isotope data from these sections, besides the carbon and oxygen. And we found there are 3 phases of these volcanic activity at the KT boundary, well recorded in the Indian section, and then correlated in these global sections. And we have got the same picture from all these areas. The flight of the Himalaya and the clockwise movement, then the opening of the Indian Ocean there that time, and detachment of Australia from Antarctica. So this happened around 65 million years back, and these are the sections which are studied for Deccan volcanism. This affected because we have data from.
We all know that Nepal is a Himalayan country and multi-hazard prone country because there are some regions. 20th most disaster prone country in the world. So this is very highly prone country and due to fragile geology and steep topography. And ranked fourth vulnerability to climate change. So it is also very vulnerable in impact of climate change. And 11th in earthquake and 13th in flood hazard among 200 countries. So Nepal is very vulnerable country. So if we look at the disaster type, although epidemic and earthquake are in forefront, but yearly disaster, landslide and floods, they are very yearly disaster and impact is so huge. I don't like to read every statistic here, this is in the slide. So Nepal is very, it shows that Nepal is very vulnerable in landslide and flood. So, located between main frontal thrust in south and main boundary thrust in the north. So, if we look at the tectonostratigraphic of the Siwalik, so it is in the between main frontal thrust in the south and main boundary thrust in the north. The figure clearly shows about this. So how is Siwalik in Nepal? It comprises 14.78 land extended 8 km east to west. So it is along east to west of Nepal. provided environmental services. This is very important. Chure provide environmental services to the 60% people live in Shivalik, Bhavan, Tarai and Madhesh. So this is very important. So Shivalik mountain is very important in Nepal and its sustainable development. So how this mountain is interconnected with Bhavan, Tarai and Madhesh, which are very, very vulnerable to disaster and geo-hazard, mainly landslide and flood. So if we see the Shivalik formed by fluvial sedimentary rocks, very unconsolidated topography and very poor capacity to percolate high intensity rainfall caused due to landslide, mudslide, erosion, rockfall and many other disasters. So it has very low capacity, very slow, unconsolidated and low capacity to percolate the rainfall and that caused several disasters. Understand the context.
Author Dr. Motilal Rizal, Board Member of President Chure Tarai Madhesh Conservation Development Board. Again, Geologist Premnath Pode.
I would like to welcome all of you for my presentation, which is entitled Issues and Challenges Managing Riverbed Materials in Chure Tarai region. So, I would like to just make the rise of the things from the last presentation because we have the very minimum budget to conserve the area which we can really then show the impact. That means we are trying to conserve with only 20 to 25% available budget, less than that was planned under our master plan, which was also led by Dr. Vinod Bhatta, who is the co-chair of the session. And you have any questions or comment on Chure overall, not only about the presentation and this thing, but overall. After the session, I think we will have some time, then at that time we can openly discuss the things. So, just giving the overview of my presentation, so many things already came in previous presentation. So Mahabharat, one friend once asked me, why should be there is a Mahabharat Conservation Board? Because you are the Chure Conservation. He was joking, but after that, I realized I think this is the agenda we should think about very deeply. Why we need to conserve Chure, not Mahabharat, because whole Nepal we need to conserve and develop for our prosperity and development. This is, and my other one is rivers and river system management in Tarai Chure. I just abbreviated the Tarai Chure into CT, so not to make any confusion. And riverbed materials in Chure Tarai regions, and lesson learned from managing riverbed materials and managing riverbed materials in new federal government structure, because we have only one government system, one pillar system before, but now we have the 3 pillar systems. So, and what's the problem and issue emerging under the 3 pillar system of the government? So this will be, I will be also talking about that. And at the end, some issues and challenges for managing riverbed materials. So Himalaya is the youngest of all the mountains, but Chure is even the youngest of these all mountains. So it is young, fragile, and also in the active mountain range, and it is regarded as a Chure conservation area. So this already came as with previous presenters, so I am not going to talk much. So this is the evolution and realization, how long it takes until the government really form one body with power of managing and implementation or forming the policies. And
subsequently, there's work done in Sikkim on the Lesser Himalayan duplex, which is one of the structures which is well established in the Himalaya today. So if you take all of this together and along with some of the frontal work we've done, the Darjeeling, Sikkim, Tibet Himalayan wedge looks something like this. You have a Kanmar dome here, Lesser Himalayan duplex, and the frontal MFT. And of course, again, we have district faults that sold with the main Himalayan thrust. So the other thing we have to worry about when we look at deformation is time, which ranges, so the deformation in time ranges from geological scales, from billions of years to about 150,000 years, to geophysical data, which is essentially the younger part of the deformation. The youngest part of that is GPS, which today, if you've started in 1993, would give you about 25 years of data. So Juga Dun, this is the Kosi River exit. and that's Gorubathan recess, where actually the mountain front recesses by about 15 kilometers. And there is a tear fault which basically separates the two. So by setting up, so that's a cross section along AB, this much, and that's the Chinese and Tibetan part. So these are the stations along AB. So if you take, if we just take all the stations and look at the velocities, they all point approximately anywhere from 50 to 20 millimeters per year towards the northeast, and that's the global ITRF scale.
I'm Kundaraj Kaudel from Technicak Session DVD, Nepal. Now I would like to present my presentation on the margin of hand thick limestone sedimentation, implication for the tectonics in the Kathmandu Basin. Today I would like to present in the following ways: introduction to the Kathmandu Basin sediments, objective of this study, geological structures, soft sediment definition, records and its significance, and paleoclimatic and paleotectonic control on drainage of the Kathmandu, ancient Kathmandu lakes, and some conclusions. Next one is origin, causes of hand sediments and tectonic and or climatic implications. Actually, Kathmandu Basin field sediments have many hidden history about the tectonics of this region, depressional environment and paleoclimates. So this is important for the study. Rise of the Mahabharata rays related to the recent tectonic of the Himalaya causes dating of the Proto-Bagmati River, which was flowing from north to south of the Kathmandu basins. After the damming of in the southern part of the Kathmandu basins, alluvial fluvial condition of the Kathmandu Valley basin gradually started to change. Marginal lagustine and forward lagustine conditions. So basin field sediment is divided into broadly three sedimentary phases. In the north, it is a fluvial-deltic phases, Gokarna formations. In the center to the south is fluvial lagustine phases, and in the southern margin it is fan phases. It is called E-type formation. All these sediments are deposited before the lake succession. During the lake succession, dating stage of lake succession, it means delta deposits, and fan and fluvial succession during and after the lake deposits.
First of all, the geology of Nepal Himalaya, I think everybody knows that the geologically it divided into 5 tectonic zone and one first of the tectonic zone, higher Himalaya, lesser Himalaya, Shivalik and Gangetic Plain. And everybody knows that all the river systems from the Himalaya flowing through the from the higher Tibetan, higher Himalaya, lesser Himalaya and Shivalik, and finally in the present condition deposited in the Gangetic Plain. But as you know, the Shivalik is an ascent Gangetic Plain. So all the stratigraphy of the Shivalik group, and stratigraphically it is divided into 3 groups: lower, middle and upper. And overall it's that the lower is the fine grade sandstone and middle is the coarse grade and upper is the conglomerate deposit. That's why you can see the overall the porosity patterns. In the Konal River section, there are several studies have been done previously, and geological stratigraphy Department Mines and Geology 1987, 2003, and I have also studied the stratigraphy, and which is published in Nepal Geological Society 2012, and magnetic study by the Gautam and Fujira 2000, and fluvial phases is Hugh et al. 2005, and I've also done the phases analysis, and which are published in NGS in 2016, and also near isotope study and organ mica dating, and zircon as dating, and finally appetite physical track analysis. So till date, no whole rock geochemistry has been done in the Konal River section, which I have analyzed the major element and trace element from both 97 sample. And for the discrimination of the different element, I have used the variation distribution diagram, and this diagram shows the relation between the air to O3 to the element variation between sample and comparative basis association. This diagram shows the effect of quartz and carbon dilution quartz.
सकूं म नेपालीमै बोले यो इंग्लिश बोल्दा कता कता डिट्याच भएको जस्तो लाग्छ, अंग्रेजी बोल्ने नेपाली नबुझ्ने कोही हुनुहुन्छ जस्तो लागेन, त्यही भएर सबै नेपाली छ। अब टेक्निकल एस्पेक्ट हामी कस्ता भएछौँ भन्दा अब यहाँहरू सबै जियोलजिस्ट हुनुहुन्छ, वैज्ञानिकहरू हुनुहुन्छ, सबै यहाँलाई जियोलजीको बारेमा केही भन्नै पर्दैन, यहाँहरू सबैलाई थाहा छ त्यो। र त्यसपछि यही टेक्निकल भन्ने चिजमा थुप्रै आउँदा रहेछन् अरू पनि। अनि अहिले काम हेर्ने हो भने तपाईँहरूको आफ्नो विधामा विषयमा हाम्रो विधामा हामी सबैले गरिरहेछौँ, तर जब त्यो पिपुल्स पार्टिसिपेसन र पिपुललाई जोड्ने कुरा आउँछ त्यतिखेर चाहिँ हाम्रो के हुँदो रहेछ, टेक र निकल हुँदो रहेछ। टेक्नलाई त्यहाँ गयो, त्यसपछि निक्लेपछि हाम्रो काम सकियो भने जस्तो हुँदो रहेछ। उनलाई काम लाग्ने टेक्निकल एस्पेक्ट चाहिँ हामीले निकाल्न सकिरहेको छैनौँ कि भन्ने एउटा समस्या हो। अब यो चुरेको समस्या प्रकृतिको समस्या होइन, जियोलोजीको समस्या होइन। प्रकृति यसै गरी बनाएको छ, यसै गरी चल्छ, यसै गरी जान्छ। तर हामीले बिगारिदिएको, हामीले गरिदिएको चिजहरूले चाहिँ त्यसलाई असर बढी गरिरहेछ र हामीलाई नै त्यसले फेरि असर गरिरहेछ। यो सबै सम्झिँदा चाहिँ कहिलेकाहीँ कथा याद आउँछ। कालिदास यस्तो विद्वान थिए जसले चाहिँ नि फेदमा के अरे टुप्पोमा बसेर फेद काटिरहेको थिए। हामी नेपाली चाहिँ प्रायः त्यस्तै भएको छौँ कि प्रकृतिले सबै चिज दियो, अब हामीले त्यो प्रकृतिको बारेमा बुझेर त्यसलाई अनरै गर्न सक्यौँ। अर्को भाषामा भन्दा त्यही सुनको फुल पार्ने कुकुरी हामीलाई प्रकृतिले दिएको थियो, हामीले चाहिँ अन्डा लिएर पुगेन, त्यसैलाई काटेर सब झिक्न खोज्या हो कि सबै चिज एकैचोटि, सब चिज एकै ठाउँबाट। कुनै पनि चिजको लागि समय चाहिन्छ, समय छैन, हामी सबै अधैर्य भयौँ। चुरे डिग्रेडेसन आज मात्रै सुरु भयो होइन, वर्षौँको थियो, अलिकति प्रयास भयो, केही भइरहेछ। अब त्यसैमा हामीले के गरौँ, एकातिर हामीलाई ढुङ्गा पनि प्रशस्त चाहियो, अर्कोतिर काठ पनि तुरुन्तै चाहियो, त्यहाँको जग्गा पनि अब सरकारी जग्गा जे विकास गर्नलाई परे पनि त्यहीँबाट चाहियो, हामी अरूतिर जान नसक्ने। अहिले एकातिर अब फन्डिङका कुरा गर्नुहुन्छ भनेदेखि फन्डिङ पुगेन भने फन्डिङ कहाँबाट पुग्छ, कहाँबाट आउँछ र? फन्डिङ जे जति छ त्यसैलाई मोबिलाइज गर्ने हो, हाम्रो लागि कहीँबाट त्यो आकाशबाट बर्सिने चिज पनि होइन। सायद हामी चाहिँ अलिअलि विदेशीले दिएको अनुदान र ऋणलाई चाहिँ नि फन्डिङ भनेर दङ्ग परेर त्यसका पछि दौडेर हाम्रो कयौँ कार्यक्रम पनि बिग्रिन थाले हो कि जस्तो लाग्छ, आफ्नो स्रोतभन्दा बाहिर गएर सोचेर। प्रकृतिले दिएको छ त्यो ढुङ्गा बेचौँ न, त्यही ढुङ्गा गिट्टी बालुवा त्यो स्रोत हो, तर त्यो स्रोत कति निकाल्ने, कहाँबाट कसरी निकाल्ने बिर्स्यौँ हामीले। त्यति मात्रै गर्दै पुग्छ तर त्यो गर्दैनौँ। निकाल्न दिएपछि सबै सोरेर तीबाट मेरो नजिकबाट, त्यो नजिकबाट गएर हामीले धेरै चिज बिगारेका छौँ, त्यसैले पनि डिग्रेड गरेका छ। ज्ञान नभएर गरेको फटाइ चाहिँ माफ हुन्छ, तर यहाँ ज्ञानीहरूले गरेको फटाइलाई के गर्ने? जानिकन अर्को पुस्तामा के हुन्छ भन्ने त छोडिदिनुहोस्, आफै म त यहाँ बस्ने होइन, के होइन, कमाएपछि भइगयो भन्ने जस्तो। एउटा सानो संसदको एउटा समितिले अध्ययन गरेका थियो, बुटवलको तिनाउ खोलामा गिट्टी बालुवा एक्सपोर्ट गर्दाखेरि सरकारले 1 अरब रेभेन्यू पायो, तर त्यसले बिगारेको बाटो बनाउन 11 अरबको लगानी गर्नु पर्यो। यस्तो खालको लगानी र यस्तो खालको प्रतिफल पाउने हो भने हामीले त्यो प्रोजेक्टमा किन लगानी गर्ने? बालुवा गिट्टी ढुङ्गा अहिले बन्द भएको छ, एक्सपोर्ट बन्द भएको छ भने के आपत्ति भयो त भन्न सकिएन र? साधारण हिसाबले भन्दा हामी चाहिँ कस्तो भयौँ भन्दा हरेक चिजमा अब अहिले एक्सपेरिमेन्ट चलिरहेछ। 3 तहको सरकार हामी कसैले कहिले भोगेका थिएनौँ। कहीँबाट ल्याएर चट्ट राखेको मोडल पनि होइन कि त्यहाँबाट सिकेर ल्याएर गरौँ। अब अहिले सरले म्यानेजमेन्टको कुरा निकाल्नुभयो, इन्स्टिट्युसनल मोडलको कुरा निकाल्नुभयो। अब म उहाँहरूको कन्सर्नलाई चाहिँ नि म धेरै धेरै एप्रिसिएट पनि धन्यवाद पनि भन्छु। तर साँच्चै भन्ने हो भने एकाडेमिक एक्सर्साइज बाहेक तपाईँ हामी कोहीसँग पनि प्र्याक्टिकल अनुभव छैन। 3 देखि चुरेर तराईकै बेल्टमा रिसर्च र अध्ययन र काममा बढी लागेको छु। त्यो बेलादेखिको टाइमलाइनमा चाहिँ मैले पाएको उपलब्धि एउटा त्यो हो। यो आजको आजै चेन्ज हुँदैन। र अर्को फेरि हाम्रो सबभन्दा ठुलो प्रब्लम चाहिँ एटिच्युडको। के तपाईँहरू जियोलोजिस्ट, उहाँ फरेस्टर, उहाँ एग्रिकल्चरिस्ट, उहाँ चाहिँ लाइफस्टक एक्सपर्ट, भेटेरियनहरू, त्यसपछि गएर फरेस्ट्री अनि ल्यान्डका कुरा आउँछ, त्यसपछि जलस्रोतका कुरा आउँछ, सिँचाइ, यी सबै एक्सपर्टिज बसेर इन्टरडिसिप्लिनारिटी देखाएर जोइन्टली हामीले कहिल्यै काम गर्न सिक्यौँ। आजको दिनमा त्यो च्यालेन्ज हो हामी सबैलाई। हामी सबै सँगै बसेर एउटा सल्युसनमा जानु पर्यो र बेस्ट सल्युसन के हो? मिनरलले के दिन सक्छ, जियोलोजिकल एक्सपर्टिजबाट हामीले के पाउन सक्छौँ देशको लागि, फरेस्ट्रीबाट के कति कसरी लिन सक्छ, सबै बसेर एउटा जोइन्ट प्लानिङ, जोइन्ट म्यानेजमेन्ट, जोइन्ट अर्गनाइजेसनमा जाने खालको सोचमा आउनुपर्ने बेलामा हामीलाई के सजिलो हुन्छ? A to B लिनियर रिलेसन खोज्न सजिलो छ। टाउको दुख्यो, एउटा डक्टरले प्रिस्क्राइब गर्छ सिटामोल, त्यो त डक्टरलाई किन्छ, तपाईँ हामीले गर्दै भइगयो। त्यस्तो लिनियर रिलेसनको लागि कोही पनि चाहिँदैन। अहिलेको आवश्यकता सबै सँगै बसेर गर्नुपर्ने छ। मेरो बुझाइ चाहिँ त्यही भएको छ। सायद म गल्ती होला, यहाँहरूको अगाडि यो भन्नु अब मेरो कम बुद्धिले पनि भनेको होला, तर यो चिज विचार गरेन भने चाहिँ अगाडि जाँदैन कि। र फेरि अर्को एउटा दुर्भाग्य हाम्रो चाहिँ के छ भने म मेरो एक्सपर्टिज र मेरो काम जान्दिनँ। प्रधानमन्त्रीले के गल्ती गर्यो म उहाँको कमेन्ट क्रिटिसाइज गर्न सक्छु, उनले गर्ने काम मलाई थाहा छ, मेरो काम मलाई थाहा छैन भने जस्तो देख्छु। अब यी सबै चिजलाई गरेर धैर्य पनि चाहियो, कहाँ गल्ती भयो त्यहाँ पोइन्ट आउट पनि गर्नु पर्यो, त्यसलाई चाहिँ सुधार्नु पनि पर्यो, र जसलाई सुझाव दिन्छ उनले ग्रहण पनि गर्नु पर्यो। डिफेन्सिभ भएर हामीले गऱ्यौँ भनेर मात्र हिँडेर भएन। अब हाम्रो यी खालका कल्चर र यो खालको सोचमा कहिले परिवर्तन हुने हो? अब एकातिर सोसियोलोजिस्ट आउनुहुन्छ, तिमीले के जाने छौ, एन्थ्रोपोलोजिस्ट आउनुहुन्छ, यो सबै हाम्रो एरिया हो, अब हामी सबै सँगै बसेर गर्नु छ भन्दैनौँ। अब चुरे विनाशको लागि गरिएका क्रियाकलाप, एकातिर चुरेको लागि भनेर यो प्रेसिडेन्ट चुरे कन्जर्भेसन भनेर यो समितिबाट लगानी भइरहेछ, अर्कोतिर त्यो यसको लगानीलाई नेगेट गर्ने, यसलाई खतम गर्ने किसिमका लगानीहरू अरूतिरबाट भइरहेछ। राजधानी बसाउनु पर्यो कसैको, सरकारी जग्गा पकडमा आउने, पैसा नतिरिकन आउने कहाँ छ? चुरे बेल्ट, तराई बेल्ट, त्यो भावरको बेल्ट, रिचार्ज जोन जहाँ छ गोदावरीको भावरमा चाहिँ बसाइँदैछ 7 नम्बर प्रदेशको राजधानी। अब रिचार्ज जोनमा राजधानी बनाउने र बसाउने भएपछि त्यो अवस्था त्यहाँको के हुन्छ होला? स्पेशल इकोनोमिक जोन भनिएको छ, सबै बस्दैछन् चुरेकै बेल्टमा, यो लगानी हो के अर्थ होला? स्कुल बन्नु पर्यो, युनिभर्सिटी बन्नु पर्यो, या चाहिँ ठुलो हस्पिटल बन्नु पर्यो, केही पर्यो, चुरेकै जग्गा, त्यो भावरकै जग्गा दिने भनेको के होला? त्योभन्दा पनि डरलाग्दो अहिले अब एउटा एयरपोर्टको कथा भइरहेछ। हाम्रोमा चाहिँ एयरपोर्ट त्यत्रो चाहिने नचाहिने के हो कसो हो? 50 वर्षपछिको एभिएसनको हिस्ट्री के हुन्छ हामीलाई थाहा छ। अहिले कल्पना गरिँदैछ सर्कुलर रनवेको, अब यति लामा लामा ठुला ठुला रनवे नराख्ने भनेर, बाई 2050 चाहिँ ग्लोबल्ली त्यो आउँछ भनेर। तर अहिले हाम्रोमा के छ, 2000 यो समय यति गर्ने मेलाम्ची एउटा बनाएर हामीले अहिलेसम्म पानी दिन सकेका छैनौँ। कति वर्ष लाग्यो? 3 टाइम्स अफ द प्रोजेक्टलाई मागिसक्यो। अब त्यही गरेर यस्ता खालका प्रोजेक्टहरू जसमा यत्रो लगानी हुन्छ 3 टाइम्स 2 टाइम्समा गयो भनेदेखि के चाहिँ प्रतिफल पाउँछौँ हामीले? ऋण बाहेक। त्यस्तै गरेर अरू चिजहरू, अरू डेभलपमेन्टहरूमा एग्रिकल्चरको हेर्नुहोस्, त्यस्तै गरिन्छ। सिँचाइ यति भयो, यति एरिया कमान्ड एरियामा छ भन्यो, साँच्चैको सिंचित जग्गा कति छ भन्यो भने 40% पनि छैन, उहाँहरूकै रेकर्डले भन्छ। भन्दा हामी यस्ता फट्याइ गरेर आफैलाई ढाँटेर बिगारिरहेछौँ। यो चिजमा तपाईँ हामी सबै सँगै बसेर मिलेर, टेक्निकल प्रब्लम देख्दिनँ सर, मलाई माफ गर्नुहोस् है, टेक्निकली हामी सबै साउन्ड छ, हामी सबैसँग प्रब्लमको सल्युसन छ, तर यो मानिस भन्ने चिजलाई म्यानेज गर्न, यो समाज भन्ने चिजलाई म्यानेज गर्न चाहिँ गाह्रो भएको छ। यो दुईटालाई नमिलाइकन चाहिँ कुनै पनि डेभलपमेन्ट हुँदो रहेछ। गरिब र गरिबी देखाइन्छ, फट्याइ गर्ने चाहिँ जान्ने र धनी बढी छ नै जस्तो लाग्छ।
म यो संस्थाको अध्यक्ष भएर आइसकेको बेला म सुन्ने गर्थेँ सबभन्दा प्रयोग भएको ठाउँ र सबभन्दा बढी एक्सप्लॉइट भएको ठाउँ चुरे, तर सबभन्दा कम अध्ययन गरिएको र सबभन्दा कम लेखिएको विषय चुरे। मलाई आफैमा आश्चर्य लाग्थ्यो र आज गर्व लाग्दैछ युवाहरूको कलम पनि चल्न थालेको छ चुरेको विषयमा, अध्ययन र अनुसन्धानको विषय पनि हुन थालेको छ चुरेको विषयमा। हामीसँग अग्रज डाक्टर भट्ट जस्ता कलमका सिपाहीहरू पाएछौँ भने आज थुप्रै युवाहरू पनि त्यस्ता कलमका सिपाही पायौँ। अब चुरे जोगिन्छ भने थोरै हिम्मत आउन थालेको छ। सबै चिजलाई जोगाउने, सबै हाम्रा मोनुमेन्ट र हाम्रा सभ्यतालाई जोगाउने उपाय भनेको रिसर्च मात्रै हो जस्तो लाग्छ। र हामीसँग वैज्ञानिक आधार छैन भने त्यो चिजलाई पुष्टि गर्ने कुनै अर्को आधार हुन सक्छ। अब ती आधारहरू बिस्तारै कायम हुन थालेको छ र यस्तो अन्तर्राष्ट्रिय प्लेटफर्ममा 9औं नेपाल भौगर्भिक सम्मेलनमा नेपाल भौगर्भिक समाजले राष्ट्रपति चुरे तराई मधेस संरक्षण विकास समितिलाई पनि विषय पनि दिनुभयो, सेसन पनि दिनुभयो र हामी यो 9औं कङ्ग्रेसको पार्ट पनि भयौँ। हामी आज तपाईहरुप्रति अनुग्रहित छौं र आज गर्व पनि लाग्दैछ र मलाई लाग्छ तपाईहरुले जुन आज 9औं सम्मेलनको विषय तोक्नु भएको छ हामी मास्टर प्लानको धेरै नजिक छौँ हैन डाक्टर साहब? तपाईहरुको विषय रहेछ जियो साइन्स फर इकोनोमिक प्रोस्पेरिटी एन्ड सस्टेनेबल डेभलपमेन्ट। हाम्रो गोल पनि अलमोस्ट प्रोस्पेरिटी र सस्टेनेबल डेभलपमेन्टको लागि हेर्नु होला। हाम्रो गोलमा त्यो कुरो धेरै नजिक यही भाषा नभए पनि भावना 100% यही रहेछ र कतै न कतै वेभलेन्थ मिल्न थालेको छ। दिमाग मात्रै हैन, मुटु पनि, हेड हैन हार्ट पनि मिल्न गइरहेको स्थितिमा ह्यान्डबाट हुने जति एक्सनहरू छन् सबै अब हाम्रो एकाकार हुन्छ भन्ने मान्यतामा गएको छु र यस्तो विद्वत समाजमा यस्तो विद्वत परिवेशमा बसिराख्दा बिहानदेखि बेलुकीसम्मको उपस्थिति साँच्चीकै गरिमामय छ र म डाक्टर साहब मार्फत तपाईको समग्र समाजलाई एक्जिक्युटिभ बोर्ड लगायत समग्र जति साधारण सभा सदस्यहरू छन् उहाँहरूप्रति म नमन गर्न चाहन्छु।
Right side, you can see the sea level, how it changes with time. So this is actually HST, high stand system tract. And mostly in this stage, shale and sand deposits. And dominantly in this stage, it is more sandy, and whenever the sea level rises, it becomes more shaley. And like this, you can here see the LST, low stand system tracts at the early stage and the later stage, and you can see the transgressive surface. And here again we have another surface which is called this maximum flooding surface, when the sea level is at the peak, and then again it starts falling either due to continental rise or the rise of the bottom of the sea, or due to the sea level rise. My study area actually it is Sylhet Basin or Surma Basin. It is one of the sub-basin in the Bengal Delta, occupying large area, and it is very prospective for hydrocarbon. In Bangladesh, we have about 26 gas fields, and out of 26, near about 12 gas fields are situated here. And this is the area where we are actually studying. Our study area is this one of the anticlinal structure, and this is the area where our study is actually restricted. And we have taken 13 seismic lines. Based on that, you can see the CU coarsening up, fining up during LST, MFS, maximum flooding surface, peak at the maximum shale volume, because that is the highest depth of water when maximum shale will be deposited, and then sea level gradually falls down, and in that case, again, the alternations from shale to sand will be started.
I have collected this data, especially the KD, LNKD, calculated by the softwares, and these data I have taken from the different journals, that is XFE, XMG, XMN, and XCA Garnet, and XFE, XMG, XTI, and all these from for biotite, and this is for garnet, and this is values calculated from the software, that is your KD and LNKD. And later on, based on the observation that effect of XMG, biotite, XFE, biotite on KD, the role of KD with regression values, because this depend upon the chemistry of the minerals. And if you'll see later on, the distribution means how the equation, if you'll see the Parchuk and Leverthivar equations.
Geoscientists and the students. I'm Lalit Kumar Rai and a PhD scholar in the Sensei University, Nagano in Japan. My ongoing research on the Muxar Khola section in the eastern Nepal Himalaya. At first, the introduction. During the Neogene period, thick pile of shivalik sediments developed from the erosion of rising Himalaya were deposited by the fluvial system in the Paleogangetic basin. In general, this sediment shows coarsening upward succession, which is fluvial succession shows the fining upward succession. The Shivalik group extend all along the Himalaya, forming the southernmost hill range, and it's bounded by the main boundary thrust MBT in the north and Himalayan frontal thrust in the south. The lithostratigraphy of Muxar Khola section has not been established yet, but this section consists of all three well-asserted divisions, that is the upper Shivalik, middle Shivalik, and the lower Shivalik section, with the overall thickness of about that is more than 4 kilometers. A magnetostratigraphic study of this area has been carried out by Oza et al. 2009, indicates that this 25-meter thick middle Shivalik Muxar Khola section was deposited from 3.5 ma to 10 ma. In this study, mainly 10 lithofaces were identified in the middle Shivalik of Muxar Khola section based on the MEAL 1977, 78, and 96. These are the faces GT, which is characterized by the pebble size clust stratified in the matrix of medium to coarse grain sandstone, and the faces ST, medium to coarse grain sandstone, occasionally pebbly and thickness up to 2 meters.
This at this meeting before, and it's really a great topic. It's very important. Education, of course, we're inspiring the next generation, and then the geoheritage and geotourism is an outreach that gives broader education to a wider community. So I do want to say that we've got 5 talks, and I assume that they are all here. Talks are all 15 minutes in length, so we will give you a warning at 12 minutes. And we'll yank you off the stage at 15. So I'm kind of joking about yanking you off, but we will ask you to stop your presentation at that time so that we can keep on schedule. And hopefully, if you stop at 12 minutes, that gives us some time for questions as well. So first presentation, Harold Thomas, and the topic, massive open online courses, MOOCs, and e-learning. A case study of petrology and metamorphic petrology MOOCs on Swayam platform in India.
My topic is Massive Open Online Course, MOOCs and E-Learning, a case study of petrology and metamorphic petrology, MOOCs on Swayam platform from India. Swayam is a program initiated by Government of India and designed to achieve the 3 cardinal principles of education policies, that is access, equity, and quality. That is, these three are very, very important. The objective of this effort is to take the best teaching, learning resources to all. Because nowadays, there is a lacking of faculty members in different universities and colleges. That is why the Indian government have initiated this program, so that those students which are in remote areas, they can access through Swayam platform.
Some examples of these course sediments that has been obtained during the expedition, and these are the hemipelagic layers. Hemipelagic layers are the fine sediments that are settled down in the deep basin part, and then one of the interesting part is ash layer, volcanic ash layer. It was identified as Toba ash, and which has been erupted around 70 to 80,000 years before, around Indonesia or somewhere, and then this Toba ash were deposited in the middle of the Bengal fan, and so some fine sediments and more turbidite cores. And the deepest one, U1451, is we obtained turbidite sequences with fine laminations and some clay stones and limestones at the depth of around, the hard rocks were obtained from around 1,000 meter, and then limestones were obtained from around 1,100 meter. So before that, before the 900 or 990 meter, we obtained the Himalayan sediments.
The marker formation was transitionally overlain by test formation, and and that tiny girl standing in the background is me. And the domain, it is dominantly composed of mera sandstone and mera siltstone, and minor amount of quartzite was also observed in the middle part of the formation. And its thickness was 1,000 to 1,200 meters. The salient features of this formation is the rock. So the rock was made rock of metasandstone. So metasandstone of this stone formation was highly micaceous, and if we are lucky enough and the day is sunny enough, we get to see the shiny rocks of metasandstone, and that is how we can also distinguish between the metasandstone of Sopang formation and the stone formation. And this again lies transversely above. And talking about the structures, primary structures like parallel lamina, cross patterns, and ripple marks were observed, and all of them showed right side up direction, and structures like joint fold, foliation, faults were observed. And after plotting all the data in this chairenet, we came to know that the structure, mega structure, Mahabharata synclinarian is not symmetrical fold, and it's deeply genting and southeast trending. And talking about the metamorphism, intensity of metamorphism increased from the Marco formation to the younger Chitlang formation.
Think about the management of risk, how to mitigate and how to prevent if possible. For that, in disaster risk management, first we try to prevent or mitigate the disaster if possible, but it is not always possible. For example, earthquake is in not our hand, it occurs itself. It is on that depends upon the geology of the earth. That's why we should be ready for preparedness. We try to mitigate by preparing the people and other infrastructure to mitigate the effect of the disaster. And preparing the things is also not 100% always, and at that time we should be ready for immediate response. Immediate response means we have to mobilize the fire brigade and immediate medication, for example, and not only that, we must focus on the efficient evacuation scenarios. What I am going to tell you that I am considering the temporary shelter in intermediate place also, meaning that for sometimes there may not be sufficient space in sink, means safe place. At that time, that evacuees, those who cannot be sent into the sink, can be kept in intermediate place, relatively safe place, for example, in nuclear accident or tsunami. You go, further you go from the dangerous place, you will be the safer. That's why if we cannot send to the sink, then we have to prioritize to keep in the temporary center.